Hey students, it is Mr. Rich. Hopefully you can hear me. If I've got anybody out there, post in the comments. Let me know if the audio is coming through loud and clear. I'm Mr. Rich. I'm a math tutor here in Jacksonville, Florida. I hope that your school year has gotten off to a good start wherever you're at. I do a lot of coaching on high school math, anywhere from Algebra 1 all the way up to AP Calculus and everything in between. I do geometry, Algebra 2, lots of AP Pre-Calc, Calc AB, AP Stats. I used to be a teacher at Stanton College up here in Duval County and worked for a year at Mandarin High School. And now what I do is exclusively math coaching. So anyway, so I do these sessions here mostly for my students that I tutor, just as an extra resource for them to get some help with their homework problems. And so I've got some problems that have been submitted that I'm going to work here tonight. Now, if you're watching live and you're one of my students, you have my email address that you could send me an email to, and I'll be able to pull that problem up and work it, unless you've totally stumped me and I don't know how to work it, but I'll give it a shot. And I've got some problems that some students have already submitted to me before the session started. If you aren't one of my students, but you are watching live, certainly what you could do is put a comment in. Thank you, Cax Max, for letting me know the audio is working. You could drop a comment over here in YouTube, and we will try to work that problem. If you are going to submit one to me, one of my students, through my email address, the best thing to do is to submit it with a photograph. Just take a picture. I can then bring it over into my OneNote, which I use as my whiteboard. So now what I'm going to be doing is I'm going to share my screen here. So you'll see my whiteboard and you'll see the problems that I'm going to work here in just a second. I also do have a virtual TI-84 that I will use for some of these problems. I think a few of these problems are AP Pre-Calc problems from Unit 1. And I'll be doing a graphical solution with both the TI-84 and I'll be using the Desmos graphing calculator. I'll also work any ACT or SAT math problems. I know a lot of students just took the SAT test yesterday, and there are a lot of students prepping for the one that's coming up in September, on September 13th. So if you've been working on that and you're stumped by one of your SAT practice problems, you could submit that as well, and I'd be happy to give you a hand on it. All right, well, let's see if we can get this to work, and I'm going to share my screen, and Christina is here. She's moderating the comments, so I expect everybody to be friendly and cordial in the comment section here. This thing's also streaming to Twitter, or X, we call it, right? So, but I don't think you can submit any comments through X if you're watching it that way, but you can always jump over to my YouTube channel at Mr. Rich Math Coach is where that's at. All right, here we go. Let's see if we can get this to work. Yeah, that's it. So you can see that I've got Desmos pulled up there on the right side. Here's my virtual TI-84. Now, I think what I'm going to do, just to give ourselves a little bit more real estate and give you a better view of what I'm working on, I'll scoot this over just a tad. And this is the first question that one of my students submitted earlier last week. And it was a really good question. And kind of as soon as I read this, I kind of knew what the trick was here and why someone might be a little bit confused on this. This, I'm quite sure, is an AP Pre-Calc question, although he didn't quite say. Now, I'm going to see if it makes sense for me to go over here. Okay, so we'll do that. That gives you maybe a little bit better view. So this says here that the leading term of the polynomial function p is a sub n times x to the n power, where a sub n is a real number and n is a positive integer. The factors of p include x minus 3, x minus I, and x minus 2 plus I. What is the least possible value of n? When you look back at what they defined the leading term of the polynomial function, you can see that the n is going to be the exponent on the variable x. So really what we're looking for here is what's the degree of this polynomial. And so if you've got this, and these are the factors, notice they didn't say those were all the factors. They said they include. That's because there is an extra couple of factors. And now that I'm reading this, I'm pretty sure that I gave that student the wrong answer. And here's why. Because these right here, that factor right there is has a root that is an imaginary number. It would be I. Excuse me. It's a complex number. That has to be paired with its conjugate. So that means that there has to be another factor of x plus I. And I failed to look at that one. That's why I know that I gave the student the wrong answer here. And Jacob, if you are watching it, you maybe entered that in and thought, what? Mr. Rich told me the wrong answer. But this right here is also yields a complex root because it's got a 2 plus I right here. So it also has to be paired with its conjugate as another one of the factors, because these conjugate, I should say these complex roots, they come in pairs. So this is going to be the other one, right? The x minus, but then that has to be paired also with its conjugate right there. So that would have to be at least the factors that we have. And if you were to multiply all 5 of those together, you would get an x to the 5th power, right? X times x times x times x times x. When you were to expand that polynomial all the way out, you would get a power of 5. So Jacob, I apologize for giving you a wrong answer. I told him the answer was 4. So anyways, I'm 0 for 1 so far this year. All right, next. This is another one of my students that submitted a lesson 1.4 problem from it looks like it is definitely AP Precalc from AP Classroom. This says the rate of people entering a subway car on a particular day is modeled by this function right here. For t between 0 and 20, r of t is measured in people per hour, and t is measured in hours since the subway began service for the day. Well, the question over here says that based on the model, at what value of t does the rate of people entering the subway change from increasing to decreasing? So they're talking about the rate changing from increasing to decreasing. And this variable here is the rate. So we need to know when this function would change from being an increasing to a decreasing value. Okay. Now, and it is people per hour. So this is, it's not shown here, but this is a calculator active problem. I know it's a calculator active problem because 3 of those answers are in decimal format. So I'm going to work this 2 ways. I'm going to work this using the TI-84. Is that you, Jacob? Okay, very good. Or I'm assuming that's you. All right, then anyway, so I'm going to work this with the TI-84 because most of you, your teacher is going to be teaching you the calculator active portion in AP Classroom with the TI-84, because when you take your tests or your summatives, they're not going to allow you to have your computer open and have Desmos available. But it is true that when you take your AP math exams in May, you will have on the calculator active portion of the test, you're going to have Desmos available to you in Blue Book. So my recommendation is, yeah, learn everything that you can about how you would solve your AP Precalc class questions using your TI-84, but also learn the way to also do it on Desmos. And I'm going to do it both ways. And the reason that you want to learn Desmos now is because most of you are juniors, maybe a few sophomores, maybe a few seniors, but mostly sophomores and juniors in AP Precalc. And you're probably going to be taking the SAT and the PSAT this year. You'll have the Desmos graphing calculator, so you want to learn and train yourself on how to use the Desmos graphing calculator for the PSAT and the SAT. So what you do here on your TI-84, if you have a function and we want to know when it changes direction from increasing to decreasing or vice versa, we're going to graph it. So I have to move myself out of the way. So I think I can move myself over here. So what I'm going to do, I'll move this over so we could hopefully, maybe we could see the function at the same time. Let's see if we can move that over. Yeah. All right, so you can see the function. Now I'm going to go, what I'm going to do in my TI-84 is I am going to hit the y equals button right here. And that's where I go into my equation editor. So I have to use x and y as my variables. So there's my y fixed over on the left side. So we're now going to type in here 0.03 x to the third power and arrow to the right to get it out of the exponent minus 0.846 x to the second power plus 6.587. So if you're an Algebra 2 student or a Precalc student, I recommend doing this with me, because you Algebra 2 students have to learn how to use your TI-84 as well. 1.428. 1.428. All right, and then what I'm going to do is I'm going to double check to make sure that I entered this in correctly, because I'm probably not going to come back and take a look to see that I didn't make an error. So it's 0.03 x to the third minus 0.846 x squared plus 6.587x plus 1.428. Okay, I think I got it in there right. I hit enter, it's saved. I don't need to save it or do some sort of sequence of commands to get it to save. It's already saved. I'm now going to quit. I'm going to do second function quit. I'm now back on my calculation screen. And then what I'm going to do is I'm going to graph this, but I'm not going to just hit the graph button over here. I could at this point and generate the graph, but what I'm going to do instead is I'm going to set the window. This is what makes the TI-84 not great. All right, I have to set the window so I see the part of the graph that I want to see. And you notice that this function is between 0 and 20. In fact, when we look at the answer choices that we've got, you can see they go from 5 to 20. So what I'm going to do is I'm going to set the window x min and x max to 0. Oh, we got to be back over here. So I'm going to come back here and hit 0, enter. Let's try that again. There's my TI license. Great. There we go. So I hit 0. Try this one more time. Enter. There we go. And then 20. So that sets the left and right window for what I'm going to actually see right there. Now, as far as my y min and my y max, if I take a look at the values here, I'm not sure what to expect, but I'm going to widen it out a little bit on my y min and y max. I'll come down here and do 0 to 50. Now I'm going to hit the graph. Okay, so that gives me a good view of what I need to see. I know that my x's are spanning over here from 0 over to 20. Now, this question was, based on the model, at what value of t does the rate of people entering the subway change from increasing to decreasing? Excuse me, I'm going to have to take a drink here. I've been talking all day. From increasing to decreasing. And that occurs at the relative maximum right here, because the rate is increasing and then it reaches its relative maximum and then it starts to decrease. So we're trying to find that value right here. Now, looking at this, I'm pretty sure D is going to be my answer, because you can count over 1, 2, 3, 4, 5 right here. That's my answer. Now, I do need to show you, though, on the TI-84 how to find out this exact value. You could click the trace button. And when you click the trace button, it does allow you to use your arrows left and right, and it'll show you the ordered pair over here. But the problem with using the trace is it moves in fixed increments, and it's not necessarily going to land you. It's not going to snap you necessarily to the top. But you can see I'm about at the top, and it's 5.45. So you can see we've got the right answer. But I want to show you how to actually find the exact relative maximum. What you have to do is move your cursor just to the left of this maximum that you're trying to find. And you're going to have to use this blue calc, second function calc, and it pulls up this menu. And you have to tell the calculator that you're looking for the relative maximum, number 4. So you hit enter, and then it tells you to go left bound, meaning make sure your cursor is left of the maximum that you want it to find. And I'm already to the left. So I'll hit enter. Now it wants me to scoot over to the right. Okay, so what it's wanting me to do is to set the boundaries for the algorithm that it's about to run to find where this relative maximum takes place. So I will hit enter on the right bound, and then it asks me, do you want me to guess or do you want me to run the algorithm? Of course I do. So I hit enter, and then it runs the algorithm, and it pops me in it right there at the maximum. And you can see we have an exact number. 5.505 rounded to the third decimal. And that becomes our answer right there. Now, I just spent 5 minutes showing you how to do this on the TI-84. And if you've never done that on the TI-84, if you wake up tomorrow and you try to do it, you won't remember my keystrokes at all. That's why the TI-84, when it comes to graphing, it's just been outpaced by other technology, right? By Desmos. So let me show you how easy this is on Desmos. So I'll flip over to Desmos here. And then what I'm going to do here is I'm going to move myself back over. Let's see. How about if I move myself up here? Yeah, that looks better. Smaller me, better me. Okay, let's go over here. I'm going to now put this function in. I'm going to put in the original function for the rate of people entering the subway. And that is y equals 0.03 x to the third minus 0.846 x to the second plus 6.587 x plus 1.428. I do not have to worry about setting the window like I did on the TI-84 because I have a mouse with a middle scroll button that allows me to like zoom in and out. There. You want to look at that, or do you want to look at that? I'm going with this because I can zoom in and out. In fact, I don't have to run a series of commands to find the relative max. All I need to do is click nearby and it says, this person probably is looking for this point right here. So it snaps right to the relative max. There it is, 5.505. So 5 hours after people started entering the subway, the rate at which the people are entering is changing from increasing to decreasing. And that's our answer. So you can see Desmos takes, I'm going to say 1/10 of the time. Okay, and that's if you know how to use the TI-84. You have to first get the training on how to do it. So anyways, I have to imagine that, some number of years from now, a couple of years from now, in the classroom, there will be no TI-84s. Or I have to tell you this, there is another calculator that I got turned on to this summer called the NumWorks calculator that I'm showing you right here. Now, this is, I think it's around $100. It's about the same as the TI-84, but schools are starting to go to this. I can't even tell you who makes it, but is so vastly superior to the TI-84 in terms of ease of use and learning to use it that I can't even tell you. I mean, the TI-84 should be non-existent in 5 years by either using Desmos or this, right? This is kind of like a happy medium between a handheld calculator and Desmos. So if I was still in the classroom and I had my choice, I would definitely be using NumWorks over the TI-84. And I've been a big proponent of the TI-84. I love the TI-84. It's incredible. It does so many things. It's a calculator that can take you all the way through your college years, through Calc 1, 2, and 3. So at any rate, we spent too much time on that problem. The only other problem that I have had submitted is this third one here. And I don't think that this is a calculator active, so we can stay away from the TI-84. All right, I'm going to move myself back over to here. All right, and then I'm going to check to see if I got any more emails coming in. Nope, this is about it. Okay. Got a little note there from Jacob. Very good. Excellent. All right, here we go. So the function h of x is given by this. It says, which of the following statements is true? H has a global min between -4 and 0, global max, global min, or a global max. All right, now, here's the thing. From Algebra 2, you probably should know how to do this problem. It is from, I think it's from lesson 1.4 in AP Pre-Calc. But I'm going to show you the thought process for this, because for these polynomials, we want you to be able to do things without a graph and draw some conclusions about them. So the first thing that I know, and this goes back to Algebra 2, is that given that this is a 4th degree polynomial right here, and given that the leading coefficient is negative, the thing that I know about the end behavior of this polynomial is that it is going to be going down to the right, excuse me, down to the left and down to the right. That's the end behavior of the polynomials that have an even power, an even degree, but yet have a negative leading coefficient. So whatever the graph is doing, it is going to be going out in this direction. Now, the end behavior doesn't tell us at all what's happening closer to the y-axis. So that requires us to do some more analysis of the function. And the first thing that I'm going to do is I'm going to try to find the zeros of the function, because those would be related to the x-intercepts. And the way that I'm going to do that is I'm going to factor this function. So I'm going to take my h of x and factor out the greatest common factor, which happens to be x squared. And because the leading coefficient is negative, I'm going to pull out a negative x squared, because I know that I'm going to get a quadratic inside that inside the parentheses, and then I want to factor that quadratic. So this will become x squared minus x minus 20 when we pull the negative x squared out. Then we can factor the quadratic, and we're going to factor it like this. So this is going to be x minus 5, x plus 4. So this gives me the zeros. And again, this is an Algebra 2 move right here to factor it. And then the way that you find your x-intercepts for any function is you set y equal to 0, and then you solve for x. So when we set h of x equal to 0, and we go to about solving this equation that we've just factored, we use something called the zero product property, which says that if you've got 2 or more things multiplied together, and I have actually 3 things multiplied together, and the answer happens to be 0, at least one of them has to be 0. So what I do is I set each factor equal to 0 and solve for x. So this first factor, negative x squared, when I set that equal to 0, I get x equals 0. When I set this one equal to 0, I get x equals 5. When I set x plus 4 equal to 0, I get negative 4. Those are the 2 zeros, or excuse me, the 3 zeros, 0, 5, and negative 4. Therefore, this function is going to be touching the x-axis at those 3 points, because the y value over here, h of x, will be 0 when x takes on one of those 3 values. All right. But the other thing that we also taught you back in Algebra 2 was that there is something called a multiplicity that you want to consider when you factored a polynomial. The multiplicity is the exponent that's on the factor, or how many times the factor is repeated, right? This factor, for this x squared factor, it's a factor of x, but raised to the 2nd power. So that means it has what we call a multiplicity of 2, because it has a power of 2. The other 2 factors have multiplicities of 1. Now, why is that significant? Well, because that tells us the behavior of the function once the function is going to get to the 0. When it gets to that location, what will it do? If it has a multiplicity of 2, the function is going to behave like a quadratic. In other words, it's going to come down and it's going to just bounce off of that x-axis right there. If it has a multiplicity of 1 and you zoom in on it, it's going to look like a linear function. It's going to cut straight across the x-axis. So this is going to bounce off of the x-axis like a parabola. This is going to cut, and so will this cut through. So that's pretty much, we're almost there, ready to answer this question. So when we come over here and we just sketch our own graph, because this would be a problem on a test or a summative for which you would not have any graphing capabilities. So you would say, okay, it's going to cross the x-axis at 0. It's going to cross the x-axis at 5. It's going to cross at -4. So those are my 3 zeros that I have plotted. And then from there, what we're going to do is realize that when it gets to this 0, it's going to bounce. However, remember what I said about the end behavior? That's important because I know that the end behavior was out here, down to the right, down to the left. So what this function does is it's going to come from down here. Since the multiplicity was 1 at that 0 of -4, it will cut through. All right. Only got a little bit left here. I have to reach around and get a little bit more. It's going to cut through, and then it's going to have to turn and bounce off of this, because at this 0, we said it had a multiplicity of 2. So it's got to come up and turn, and then it's going to have to bounce like a parabola. And then notice the distance here. And the distance here, this distance is greater. So it's got more room to rise before it's going to come back. And it's going to come back down here, and it's going to head down in that direction because of the end behavior that we have already identified. So that right there is my sketch of what I think this thing would look like if I were to graph it. And now let's go look at the answer. They were wanting us to find the location of either a global min or max. Well, right away when we found out that this had a negative leading coefficient with a 4 even power on it, and we then determined the end behavior, we knew that there was not going to be a global minimum. A and C are out. You can't have a global or an absolute minimum when the function is heading down towards -infinity along the y-axis. I mean, those are out. The question then became, where was this global maximum going to occur? Was it going to occur here at this hump, or was it going to occur at this hump? And we can draw the conclusion that because there is more room for it to rise here between the 0 and 5 than there was between the -4 and 0, that it's going to rise more. Therefore, my answer has to be.
But you didn't ask me.
How'd you know I needed this?
Because you told me.
Okay, thanks.
How come?
Huh?
How come
Because I'm on right now. I'm on with some students right now. But thank you. So somebody just delivered me some water. Okay. Anyways, so we know that this global maximum occurs between 0 and 5 right here. So D is going to be my answer. Now, what you students in AP Pre-Calc, and I'll say also Algebra 2, what you have to do, right, if you were trying to learn this material so that you can keep advancing to higher levels of math, you have to continually be making connections between things analytically when you're looking at equations and looking at graphs. You have to be able to make connections between the two. Also, those of you that are in AP Pre-Calc, you already know that there's a third way that you have to make connections, and that's in tables. So in AP Pre-Calc and in AP Calc, we're always asking you questions about functions in one of 3 modes. We're either giving them to you as an equation or in function form with no tables and no graphs, or you get a table and no graphs and no functions, or it's just a graph and you don't get the other 2. It's one of those 3. So when you're working these problems like this, after you think you've done all that you would need to do on a test question, go ahead and graph it and see, did I get this thing right? And you know how you don't want to graph it when you're just trying to check to see? You're not going to graph it on the T84 because time is precious, right? I don't want to spend 5 minutes making a graph. So I'm going to go to Desmos, and I would graph this function to see what it actually looks like. Were we even close? So I'm going to use both hands and type it on my keyboard. And the keystrokes that Desmos uses, if you've ever used Delta Math, the keystrokes are the same. So let me move myself over so we can look at this. And let's scoot that over. So, all right, so I'm going to go ahead and type this in. But my point was, I forget what my point was, but you want to, I'm using both hands here typing this in, and I'm going to see what this thing looks like. So I'll spread this out just a bit, make sure we got it right. I think I have this graphed right. And so there's the function right there. So it bounces, right, like a parabola. You know, even when you zoom in on this, it looks like a parabola, right? That's how a function behaves with a multiplicity of 2 right next to the 0. It behaves like a parabola would be expected to behave. And when the multiplicity is 1, what does it behave like? It looks like a straight line, although we know it's a curve. This function is a curve. Very close to the intercept, it behaves like a linear function. Okay, and so there we go. So now you're like looking at this going, hey, great. I really, my assumptions were right. It did rise higher. Notice how easy it is to see where that relative maximum occurred, at what its coordinates are, where the relative min occurred, where the relative max. I can get my x-intercepts. And there you go. All right, that is the end of the questions that have been submitted. Now, what I'm going to do, I still have some time left. So I think, although we have late breaking news here, someone has submitted some problems. Of course, I am going to do these problems. So let me pull these up. I have a few SAT problems that came in. So let's take a look at those. I will try to pull these up. Lickety split. I'm going to have to copy and paste them over. That shouldn't be too much of a problem. Hopefully, these are kind of low res, but hopefully they'll be good enough for us to read them. All right, so here's the first one. Olivia, if you want to resubmit those, yeah, so you can see it's a little bit low res. Maybe shoot me some pictures. I think I probably could decipher this and read it for us, although it doesn't look. Okay, so I'll read it. This comes from the SAT Blue Book Practice Test number 5. It says a right. I know you can't read this probably. I can read it. Let me make sure that you all see the right thing here. Yeah. Okay, a right triangle. Let's go over to this side. A right triangle has legs with lengths of 21 centimeters and 5 centimeters. I'm pretty sure I can read that, but it's telling us that there's a right triangle with legs of 21 and 5 centimeters. What is the length of the triangle's hypotenuse? I think, yeah, okay. Yeah, so this is question 1. So this makes sense. It's going to be a relatively easy problem asking us for the length of the hypotenuse. I'll just call it C. I think that is a right triangle, legs 21 and 5. Yeah, okay. She's going to send it in. And then once I see it, actually, yeah, I can't even read it on the email. But what we do, it looks like if this would be a Pythagorean theorem, right? 21 squared plus 5 squared would be c squared. Since we do the SAT problems on Desmos, I'm not using the TI-84. I'm going to use my I'm going to use the Desmos as just a regular calculator, right? 21 squared plus 5 squared. I think what I was getting ready to say before the water came was that that the keystrokes in Desmos are the same keystrokes that you will feel when you're doing delta math. Most of you have worked in delta math, so if you've ever written things or typed things in there, it's the same. And I think those numbers aren't right, because this would be square. It would be the square root of 466. If I had I just think those numbers are not right. Let me see if there's another one of these that I can read a little bit better. No, these look like really good questions too. So hopefully we get these resubmitted. Okay, so while she's working on getting those to me, I want to do a little bit of pre-calc. I think I have some pre-calc here that we could do. Yeah, so let me pull a few of these problems. I wanted to do maybe some concavity. Yeah, all right, I'm going to do one of these here until we get those SAT problems pulled up. So let's come down here. Okay, now these this is material from Brian Passwater, and these are materials that he's posted on the internet for AP Pre-Calc. And if you've taken AP Calc, you've probably seen Brian Passwater. I think he's done videos for College Board for AP Classroom, but he's one of the gurus when it comes to AP Math. So these are always, I mean, just outstanding materials. I wanted to show you these problems here. Make sure that you see this correctly. Yeah. All right, this says determine if the following functions could be concave up, concave down, or neither. So what does it mean when we look at a function and we say that it is concave up? Most people identify from a graph what is concave up and what is concave down. So let me show you. You've been studying this in your first 2 weeks in AP Pre-Calc. If I were to show you a third-degree polynomial that looks like this, I think you would recognize this region is concave down, because that kind of looks like the shape of a parabola that opens downward. And we did say in, I think, Algebra 1 and Algebra 2, we may have used the word concave down. And this over here looks to be concave up in this section, which then means that there's probably a location, a specific point on the curve where it switches concavity. And that would be approximately here, about halfway, right, between the vertical distance between the relative min and max. That point right there, if that's where it switches concavity, it's called a point of inflection. Points of inflection are where a function switches from concave up to concave down, or vice versa. And so anyways, what does it mean when we say it's concave down? We can't just say, well, it looks concave down like a frown, right? That's not a math explanation as to what we're looking at. What it means is this. If you were to look at the rates of change of the function as you move left to right, now I'm going to draw little line segments on the curve to represent what the rate of change would be at those locations. So I'm going to make a little line here. I'm going to make one here, right here, and then right up here at the very tippy top, I'll make a little line, and then I'll make another line here, here, and then down here. The slopes of those red lines, of those little line segments, would be a representation or an approximation of the rate of change of the function at that point. This slope, I'm just going to estimate what it is, right? It is positive slope because I know that the function's increasing. That's a positive slope. I'm going to say that it's a positive slope of 2 over 1. That one looks like maybe it's 1 over 1. It's less steep than this one. This one maybe is a slope of 1/2. That's almost flat. Maybe it's a 1/5 slope. That looks like a 0 slope. That looks like a negative 1/4. That one is a little less negative, further negative, negative 1/2. And then that one's maybe -1. But what you notice about those slope values that I just estimated for those line segments is they are decreasing. To go from 2 to 1 to 1/2 to 5 to 0 to -1/4 to -1/2 to -1, that is decreasing. So what it means when a function is in its concave down region, its rates of change are decreasing. Now the function itself on this concave down region, and that concave down region extends from -infinity over to whatever this x value is. I'll call it a. It is concave down over that entire interval, but notice it's not increasing or decreasing totally over that entire interval, because once it gets to its relative max up here, it switches, and it switches from becoming increasing to becoming decreasing. So all that to say that to the left of this spot on the x-axis, the function is concave down and increasing. And then from this spot, I'll call this spot B, from B over to A, the function is still concave down, but it is concave down and decreasing. Okay, so concave down, the long and short of it is this. It is the region over which the function's rates of change are decreasing. And you then could figure out that what does it mean for the function to be concave up? It does mean that the rates of change are increasing because they go from negative to less negative to 0 to slightly negative to increasing positive. I meant slightly positive here, to more increasing positive. So the further right you go over here in this region, the slopes are getting bigger and bigger. So the rates of change are increasing. Now, having shown it to you graphically, you need to then in AP Pre-Calc be able to identify what that means in a table of values, which just takes us to these problems. So the first thing that I noticed if I'm supposed to determine number 22, whether this function could be concave down, concave up, or neither, I want to first notice that the x's are all going up by the same amount. They're all going up by 1. That means I have what we call, and your teacher, I'm sure, has used this terminology, or you've seen it in AP Classroom. We have what are called equal width input intervals, right? The input intervals have equal width of 1. So if the input intervals are equal width, then all I have to do is look at how much the y values are changing. That's a change of positive 1 from 3 to 4. That is a change of 2. That is a change from 6 to 9 of 3, and that is a change of 6. Those numbers that I just wrote there are the rates of change. And what are they doing? They're increasing. So I could say that f of x is going to be concave up because as the input values are increasing, the rates of change of the function are increasing. And that's what we have. What would it look like if it was concave down? Looks something like this right here. This is my inputs are going up by 1, so I can just look here and say, okay, this is going down by 32. It's going down by 16, going down by 8, going down by 4. So what are my rates of change doing? The rates of change here are increasing. right? To go from negative 32 to a value of negative 16 is to increase. You're moving right on the number line when you go from negative 32 to negative 16. So the rates of change here are increasing. So this function could be concave up. All right. And let's see if we got some problems here. I think we do. Oh, those look much better. It was 11 and 9 is what that was. Now I'm going to do one more problem over here that comes from, I believe, 1.4 maybe of AP Classroom. It was these right here. It said determine the least possible degree of the polynomial. So one of the things we do with this when we've got equal width input intervals is we are going to look at the rates of change. Equal width input intervals, rates of change here, that's a 0 rate of change. To go from negative 3 to 1 is 4. To go from 1 to 8 is 7. To go from 8 to 17 is 9. To go from 17 to 27 is 10. What I'm going to do now is I'm going to calculate the rates of change of the rates of change, because what I can do here is I know now, because those rates of change are changing, it is not a linear function. And a linear function is a degree 1 polynomial. It is not a linear polynomial. Linear would be equal width intervals result in constant rates of change. However, what I'm going to do is I'm going to calculate the rates of change of the rates of change. That's an increase in 4. That's an increase in 3. Increase in 2. Increase in 1. If those were constant, it would be a second degree polynomial. I'm going to go one more here. I'm going to go now and do the third level rate of change. From 4 to 3 is a -1. From 3 to 2 is -1. From 2 to 1 is -1. This could be at least a it must be at least a third degree polynomial, because I got constant rates of change on the third level right here. Now, if you've taken calculus, you would know that we're talking about derivatives here, right? We're going out to the third level, like the third derivative here, but this would be a third degree polynomial, because if you have a third degree polynomial and you take its derivative 3 times, you're going to get to a constant value. That's kind of what's happening here. So this would have been, if this was constant, would have been a second degree or a quadratic. I got out to a third degree. It ends up being a third degree polynomial. All right, I'm going to pick out here, Olivia, what looks to be maybe the most interesting for everybody here. Wow. Okay. Okay, I'm going to do this one, because this one I think has a little bit of relevance to algebra and AP Pre-Calc students. I will show you which one we're talking about. Thank you for sending those, Olivia. I really appreciate it. Oh yeah, that's beautiful. There we go. I'm not going to show the answer here. How about that? Let's go down here. This comes from SAT. I'm not sure which one this is from. It's one of the SAT practice tests. It shows us a parabola. It says the graph of y equals 2x squared plus bx plus c is shown, where b and c are constants. What is the value of bc? I've got 7 minutes. I'm going to spend the last 7 minutes on this entire problem, because I'm going to show you some features of Desmos that kind of would blow your mind maybe as to what you can do with Desmos. So in this problem, they're hiding the constants b and c from us, but they're giving us a lot of information about this parabola. They're giving us the 2x intercepts. They're giving us the vertex and 2 other points here. It is also no surprise that this a is a 2 right there, because you notice that when you go 1 to the right from the vertex, you're going up by 2. So it's been vertically stretched by 2. So no surprise there that that's a 2. So that's really not extra information for us. But at any rate, what the trick is here on the SAT is that if you're missing parts to one of the versions of your quadratic equation, you want to use other parts from the graph to generate a different version of the quadratic equation. In other words, there's three ways you write quadratic functions. You write them either in standard form, like this one's written, or you could write them in vertex form, or you could write them in factored form. And here I could go either with the factored form or with the vertex form. And what I can do, since I know that the x-intercepts are -3 and 1, I know what the complete function is, right? In factored form, that a that's in front is going to be the same as the 2, and it's going to be x plus 3 times x minus 1. Has to be, because your x-intercepts on your quadratic are going to be relating to the factors like that. So then what you do is just go ahead and multiply or expand the x plus 3 times x minus 1. That's going to give you x squared plus 2x minus 3. And then you would distribute the 2. 2x squared plus 4x minus 6. And then when you make a comparison between this complete version where you started from factored and you put it into standard, you now know that b is 4 and c is a -6. Therefore, your bubbled in answer here in your Blue Book app is going to be a -24 for b times c. And that would be your answer. You could try this with vertex as well. Now, I did want to show you something that you could do. I would not use, I don't think I would use Desmos for this on the SAT. But one of the things that Desmos does, it does regression. And what regression is when you give technology the ordered pairs that are going to be on a function, and then you tell it what type of function it is, it fits the function to the points. Right? You can take any function and spit them out into a table and get values for x and y from the function. But we're doing that in regression. We're doing it in reverse. We're saying, here's the points, give me the equation. Well, to do that in Desmos, you type the word table, it makes a table. So I'm going to put in all three of those ordered pairs besides the x-intercepts. I'm going to put in -2, -6, the vertex being -1, -8. The other point we have is the y-intercept 0, -6. Now, a couple of months ago, they added a feature to Desmos, which was what we call the auto regression. If you look here, I need to move myself out of the way. Sure, Hadley, thanks for coming. So let me move myself out of the way. There we go. How about if why don't I just keep myself for the rest of the time cordoned off up there. All right. So then it's got this auto regression feature right here, where if you click on this icon, it is going to default and give you a list of possible function types for which it'll do the regressions for the table. Well, we recognize this obviously as a quadratic, so we tell it to do a quadratic regression, and look what it does. It gives me the equation that fits it, which is what I had come up with, 2x squared plus 4x minus 6. Now your TI-84 will do the same thing, but it just takes 10 times as long to get the data in. Okay, that's an exaggeration. Okay, maybe 9 times as long, but you have to put the data into a table in the TI-84, and then you have to run the appropriate regression, and you have to know where it is. Your teacher is going to train you on how to do that in your AP pre-calc class, because when you get into Unit 2, you'll be doing quite a bit of regression. All right, but always keep in mind, when you get to the AP test in May, you have an option of doing your regression right here, much easier, much faster. But the point is, on the SAT, though, well, I was going to say you're under less of a time constraint. I'm going to say that's not true, because when you get to Module 2, if you're a high scorer, you're going to be in the harder Module 2. Time is of the essence, so you can do that. But when it comes to, I think what I was saying, though, is that when you're taking your AP exam, your AP pre-calc exam or AP calc exam, you're not nearly under as much time pressure as you are on the SAT. So it may not be that important. Now, I'm going to show you one other thing before I go tonight. about regression. And I am going to get rid of this quadratic regression here and delete it. It's even better than this because you can do what we call your own regression. In other words, these are pre-formatted regression equations when you do this. And that's what the TI-84 does a lot, has preset ones. You can tell it what you want the equation to look like. For example, I could tell Desmos that I want it to put this quadratic with these 3 points. I want it to spit it out to me in factored form. I would do it like this. I type in y1 because my variable in this table is y1. And then I'm going to use something called a tilde. If you look to the left of the number 1 on your keyboard, you'll see a little squiggle. It's a tilde. So if you do a shift, that key, you'll get that tilde right there. And then that's telling it that you're about to tell it how you want the equation to look on a regression. That's kind of the regression command, that tilde. So I'm going to tell it that I want it to look like this. My variable is x1 minus, I'm going to call this b, that would be my x-intercept, and x1 minus c. Okay, now I need to do minus c. And notice what it did. It gave me the values of a, b, and c, which are 2, -3 for b, and +1 for c. So by reading that, it's telling me that the quadratic is 2 for a, x minus a -3, which is +3, and then the c is a 1, so it would be x minus 1, which is exactly what I had made right there. Okay, could I tell it to do it in vertex form? Sure, I could say, no, I want you to give it to me in this form, y1 tilde a x1 minus h squared. I'm putting this in vertex form. Hopefully you recognize that as vertex form. So it shows in vertex form that h would be a -1, k would be a -8, which is the vertex, -1, -8. Okay, so that is the power of Desmos right there. You can tell it to give you the equation when you feed it at least 3 ordered pairs on your quadratic. All right, students, that is going to do it for tonight. And I hope this was helpful to you. And next week, I'm going to be here. I'm going to try to be here. There's maybe one Sunday in October that I won't be here, but every Sunday night, 8 o'clock. And if you're my students, you know what my email address is. I'm not going to say it here on the YouTube channel, but you know what it is, and you can get me your questions, and I'll work them in our live session. All right, everybody, have a great week. Keep working hard in your math, and I will see you next time. Bye. You're welcome, Olivia.